All right. Good morning, everybody. We're going to get started. Thanks for coming for day 2. This is the morning session where we're going to be doing SPECFEM introduction. Just to reintroduce myself, I'm Bryant Chow. I'm an assistant professor at University of Alaska Fairbanks, a longtime SPECFEM user, part-time SPECFEM maintainer. And we've run a version of this workshop a few times over the years. And so this is kind of a condensed version that's going to fit into a couple hours. We're going to be running inside of a Docker container, running Jupyter notebooks to run SPECFEM 2D and 3D, and hopefully get you all running forward simulations and generating some kernels and maybe even doing some small inversions. Before we start, I asked everybody yesterday to download our Docker container. Can I get a raise of hands of who has done that already? Awesome, more than half. So if you go, for those who haven't, in the Slack chat yesterday, I posted a link to a GitHub README that has instructions for installing that. You should have already installed Docker, so there's just a Docker pull command, depending on what system you have. So if you could do that now while I go through a couple slides, hopefully you'll have that ready so we can all start together. And online in Zoom, I put that in the Zoom chat, a link to that GitHub README as well. So if you could please do that so that we can get started after the slides. The time's limited, so I'm not gonna spend too much time on slides. Just wanted to give a kind of a brief overview introduction of SPECFEM so that you have an idea of what we're going to be doing this morning, the tool that you're going to be using. Full disclaimer, these are not my slides. These are from Daniel Peter, who is currently the lead developer of SPECFEM. He gave this talk during our 2022 users workshop a couple years ago. So just like 5 minutes of slides, and then we'll jump into running some stuff. So the outline of this talk goes just history of SPECFEM, kind of the code repositories and where we're at as a community. And then I might not go over those applications. So he started off on a cold and cloudy day in 1995. This looks like in Paris. Dmitry Komatic, who was one of the founders of SPECFEM, was taking a class on spectral elements. Here's some of his notes from that day. And he decided at IPGP to code this up for seismic waves. So it's, spectral element method, a general numerical method for solving differential equations on computers. And so Dmitry Komatic wants to apply this to seismology. And this is kind of the precursor or birth of SPECFEM. Ewan Trump, who was at Harvard at the time, hears about this, gets interested, and says, yeah, let's write a paper. Let's bring spectral element method to the world of seismology. And so they publish their seminal 1999 paper introducing spectral element method for seismic wave propagation simulations. And really what I find super interesting and cool to be a part of is that things like SPECFEM, programs like SPECFEM, which are trying to simulate seismic wave propagation at a variety of scales, have really been moving forward hand in hand with the pace of computational technology. And so SPECFEM really has been driving a lot of development in computational hardware, in the size of computers, and what kind of problems we can solve. So here's just one paper from 2001 where they're talking about putting SPECFEM on a cluster. In 2003, they won the Gordon Bell Award for a huge Earth simulation on a terabyte cluster. And that brings us today, where we have SPECFEM in kind of its currently most mature form. We have 3 different versions of the code. They are all similar, kind of built on the same bones, but they are all kind of catered to solving different problems at different scales. Maybe you've already heard of them, but we've got SPECFEM 2D, which is solving spectral element problem on a 2D domain, 3D Cartesian, which is Cartesian domains, and then globe for large global simulations. And they each have, their own kind of optimizations in order to best solve these problems at these scales. Everything lives on GitHub. These are old links. Actually, we've now rebranded under the SPECFEM organization, but you can find them all there. We've got a pretty active community on issues and discussions. And here's a list of contributors. I think I'm going to stop the slides there and maybe just mention a couple of things as well about the current state of development of SPECFEM. Currently, Rohit Katkar at Princeton University, who is a research software engineer, is working on SPECFEM++, which is a complete ground-up rewrite of SPECFEM in C++ using the Cocos framework. And so the idea there is that we're trying to merge kind of all scales and all codes together into a single code base that is built from the ground up as a kind of a research software code. And it's built on this Cocos framework, which allows essentially plug and play into different architectures like CPUs and GPUs. And so that is currently in development, and we're very happy to see that SPECFEM will be kind of moving forward with the development of computational infrastructure. Okay, I'm going to stop slides there, and we're going to jump into doing stuff. Let's see. So like I said, it sent you this README for downloading the Docker container. I'm going to assume that you are pulling or have already pulled the Docker container, but maybe I'll just kind of run through the instructions just to explain what we did. We saw Docker containers yesterday. Ian gave a really nice talk on kind of what they are and how they're used. And so we've taken this idea and we've put SPECFEM 2D, 3D, and a couple Python tools that I work on into this container so that we don't have to fuss around with downloading and compiling software. It is a bit big. It's about 4 gigabytes. Apologize for that, but we'll delete it at the end of the day so you free up some space. We had to put Conda in there to do some Python stuff, and so that's kind of big on its own. So maybe I'll just run through these instructions on my own, and you can follow along so that we all get to the same page with the open Jupyter notebooks. And then I'll pause there to make sure everybody's with me. So, yeah. We're doing all this local. So all this will be on your local computer. Okay, so the first thing we want to do is open Docker. If you're on a Windows or a Mac machine, that means you're just going to look up the Docker app. So for me, I have to look up, let me hide this. Else check that. For me, I'm going to Spotlight and looking up Docker and opening that up. That'll just be running in the background to just make sure Docker's going. For people on Linux, there's a command here, systemctl start Docker, that you would run in your terminal. Let's make sure. Oh, I've already got Docker running. Yeah, assume we already pulled the image, so we're not going to go over that. But if you haven't, this is the command. There's different commands for either Mac Intel chips, which is the old version of Mac, I think prior to 2021 or something. Windows machines and Linux machines, there's a separate pull command. And then for those who have Apple Silicon, which is the M1, M2, or M3, there's a the section 3B tells you how to pull the image.
Does everyone know what kind of chip in that?
Yeah, if you bought your Mac probably in the last 2 or 3 years, it's likely an M chip, silicon chip. And then what I've asked you to do in step 4 is to just make an empty working directory. What Ian talked about yesterday is that, the container is its own self-contained thing. And so any work you do in there, if you don't end up saving it and you close and delete the container, then you lose all that work. So you talked about binding. We're just going to make an empty directory on our local machine and bind that to the container so that all the work that we do in the container actually just gets saved directly to our local. And you can also delete that at the end of the day if you don't want it. But just to make sure that, if you do something interesting or something that you want to keep, that it just has been saved already. You don't have to ask how to download it. So I'm opening up a terminal. Double up here. And I put an example path here. This is just some work directory that I've created for the workshop. You're welcome to put this wherever you want on your machine. Yeah. I did yesterday. It should be, if you scroll up a bit, I've posted that link. And if anybody, maybe somebody can post it. Thanks, Felix. Okay. And so now you're hopefully in your empty working directory. Please make sure you're in there because when we bind, we're going to be dumping a bunch of files into this directory. So I don't want you to dump it into your home directory or into your pictures folder. Just make sure you're in this working directory wherever you've set it up. And then we're going to run this command in 5, which is this Docker run command. There's a little button here if you want to copy that directly. And just paste that into your terminal. And cross your fingers. Hope that runs. Cool. And like yesterday, we saw opening Jupyter Notebooks. Hopefully you're all familiar with that. It's going to give you a bunch of links at the bottom to access it in your browser. You're going to want to click the one that starts with 127. And that'll open up your Jupyter Lab. I'll pause there, make sure that we're all in Jupyter Lab, make sure everybody on Zoom's on Jupyter Lab before we proceed into the notebooks. Yeah. The password. Do you already have a Jupyter instance open somewhere, like a Jupyter Notebooks open? So yeah, if you've already, hopefully that is that issue. If you already have Jupyter Lab open somewhere, you're not going to be able to get into this one. So please close already open Jupyter Notebook instances. Yeah, if you've got an issue, please raise your hand. We'll come around and try to help you out. I'm going to pause here and make sure everybody gets to the same state before we keep going.
Keys for the microphone. So pop up, you can just relax for minutes or so. And if you don't have that, so maybe other people help you.
Oh yeah, you can put. I don't think I did it. Yeah, thank you. So just to be clear, we are going to do this and we will do it on the computer. So you don't need to plug into the application service or the staff computer. This is between your local. Yeah, just for those on Zoom, I'm repeating what Felix said. We're doing all of this on our local machines, not doing anything on TAC or the cloud. This is all on your local computer. Okay, thank you.
Bryant, I'm sorry, I ran the Docker run in cell 5 and I think everything's good. And then how from there Frosty Bartik was populated in my Docker desktop app. How do I get to the Jupyter Lab from there?
Sorry, you did run the Docker run command.
Yes.
Did it come up with this kind of output log on your terminal
Yes.
after you hit Docker run? Yeah, so there should be a couple links at the bottom. You're gonna want to click
Oh, I see.
that
Yep.
one.
Okay, great.
On your, and then that should open up in your web browser.
Thank you.
No problem. Everybody having any issues? Can I get a raise of hands who's got the Jupyter Lab open, ready to go? Okay, it's like most. Hopefully, if you have issues, please ask your table mates or raise your hand. We'll have somebody come around and try to help you. Yeah. Sorry, I lost you on Zoom. I'm back. Let me throw a screen share on. Carl, can you co-host me? All right, one sec. I got booted off Zoom, just trying to get screen share back up. Yeah, I got kicked off for a second. I don't think that worked. Oh, there you go. Okay, we're back. Sorry about that. Okay. So you can minimize your terminal. We're not using terminal anymore. Rest of the workshop is in this Jupyter Lab interface. So, oops. I'm gonna make that a bit bigger. Oh, wow. I think we're breaking the internet right now. Let's see. Can you see my Jupyter Lab on Zoom?
Yeah.
Yeah, okay. Thank you. Okay. We got it. So this is our interface. I'm just going to walk through kind of the interface. You probably, maybe a lot of you have already seen Jupyter Lab, but just for those who haven't, Essentially kind of like a virtual desktop, like we saw yesterday. We've got a bunch of Jupyter notebooks that we'll be running that have a combination of Python commands and Bash commands. You can access your terminal if you need to do any terminal things. We're gonna probably not work in that, or mostly in the Jupyter notebooks. And then on your left side here, you can see a number of directories. And so this is all the software that we've already installed into your container. Just to run through them from top to bottom, EdgeDocs is our workshop material. That's where we're going to go for all the workshop notebooks. PyToa is a package that I developed in my PhD, and this is a misfit quantification package. So it does data synthetic misfit, like cross correlation travel time, creates adjoint sources, has some plotting tools for running seismic inversions and analyzing seismic inversions. PySep is a data download tool, so it kind of wraps ObsPy and it gives a nice interface for kind of event-based data download and record section plotting. Originally designed for moment tensor inversions, but can also be used for gathering data for seismic inversions. And SeisFlows is an automated workflow tool that was developed by Ryan Modrak when he was a grad student at Princeton, and I took over development during my PhD. It's essentially a workflow tool that automates a lot of the bookkeeping and nitty-gritty parts of seismic inversions. It has some wrappers for SPECFEM, has some plugins like module plugins for automating things on high-performance computers. Like let's say you're on a Slurm system, it'll automatically run jobs for you and check job failures on Slurm-based systems and other job scheduling systems. We'll use that a little bit to help us run a couple of examples. And then we've got SPECFEM 2D, which is already installed and compiled. I'll maybe just open that up here. You can see the directory. We'll do a little bit of directory exploration for 2D, SPECFEM 2D. And as well, you've got SPECFEM 3D, which is already downloaded and compiled. And we've got one notebook going over 3D as well. So again, all of this is running on your local machine. Mostly we'll be doing 2D problems, small 2D problems, so hopefully nobody runs into like compute power issues. Okay. So we're going to go and open up the first notebook, which is an exploration of SPECFEM 2D, the package, kind of the parts inside of the directory and how you would run your first forward simulation. So to do that, if you could follow along, we're going to the left directory tab and clicking EdgeDocs, and then workshops, and then 2024-521 scoped UW. So for those who missed it, this is the link or the path at the top. We went EdgeDocs, workshops, 2024-521 scoped. We've got 5 notebooks in here. We'll see if we have time for all of them. Probably not, but they're there for you to explore as well. A couple of them have exercises. We'll have some time today to let you play around with running your own forward simulations and trying to run your own inversion. And then that README that we use to download the container is down at the bottom there. And this is all hosted on GitHub as well in the link that I posted. So we're going to open up Notebook 1, Intro SPECFEM. All right, so hopefully everybody's at Notebook 1. And like I said, this is an intro to SPECFEM 2D. So kind of assumes that you've heard about SPECFEM, you've never run it before. Let's say you git clone it from GitHub and you're like, what do I do now? So this is a little bit to bring you from kind of that stage into running your first kind of example forward simulation. This one is kind of pre-filled, so we'll just kind of walk through the steps and I'll explain as you're running cells on your own notebook. And then just some bookkeeping for Jupyter. Likely you're all kind of familiar with this, but if you want to run a cell, you can click it and hit the play button. That's what that says. If you want to run everything, you can click the double play button. You can also hit Shift Enter. Sorry, yeah, Shift Enter, something Enter on your keyboard to run a cell without having to use your mouse. Okay. So we're starting the tour, and we're going to run that first cell, which is just importing some notebooks, or sorry, importing some dependencies that we're going to use to help visualize and look at some data for our example problem. And it's going to put you in the correct directory. So it's putting you into that SPECFEM 2D directory that is already pre-installed and compiled. And just doing an ls command, you can see there's a number of other subdirectories in there. You can see some configuration and some log files that came out of the make command. This is a Fortran-based code, so there's make files in order to compile the code. You can see a couple other things, and we're going to talk about we're just going to talk about kind of the most important things, the things that are important for you to actually run a simulation. So in 1A, we're running ls bin, and the bin directory, bin stands for binary, is where all of your compiled executables are. So we've kind of skipped over the technical part of compiling the software. That is very system dependent. You're going to have to do that. You know, if you run this on a cluster, you're going to have to compile it for your cluster with specific flags. And there's not enough time in a workshop to try to get everybody to that state, which is why we're using containers. So let's just say you've already done the compilation. And so all of the executables that SPECFEM can create are stored in this bin directory. This next section says probably the most important ones for the forward simulation, and these are very similar for 3D and 3D globe as well, are MESHFEM, XMeshFEM 2D, which is MESHFEM, which is the internal mesher. So I will explain a little bit about meshes and models in a later part of this notebook, but just the idea is that, you know, we need kind of a numerical framework in order to run our simulation, in order to define our domain. Let's say, you know, you want a domain of like Seattle Basin, you need some kind of mesh that helps you define what that looks like to the solver. And then SPECFEM 2D is the actual solver. So this is the code that essentially solves the seismic wave equation within your domain in order to simulate seismic wave propagation. Some other ones, that's a holdover from previously. Some other ones are XSmoothSem. So often, you know, when we're running the inverse problem, we need to do some things like regularization in order to make our updates to our model kind of more stable. And so there are utilities within SPECFEM in order to smooth volumetric files. So you can imagine you have some kind of update that you want to put onto your model that's kind of blocky and has some artifacts from, you know, some numerical artifacts. There are some utilities in order to smooth those away, in order to make sure that things are stable. And then there's some other utilities in order to kind of deal with the fact that this is a distributed problem. So we have our model is being distributed to a number of different processors. And so there are, you know, utilities in order to bring that back together into a single like file or a single utility in order to kind of do the science afterwards. So this is just really broad overview, just to give you an understanding that there are, besides the solver and the mesher, that there are a number of kind of auxiliary utility functions within the package that help you better run the forward and inverse problems. If we run this next cell, this is usually just how you run these executables with MPI. If it's compiled in serial, you can run it with /. But if we run that, this is just gonna fail. We know that, but kind of gives you an example of, you know, if you're confused about what a binary does, you can try to run it, let it fail, and it'll tell you, hey, these are the input arguments I need in order to run properly. So that's just kind of an example of how you would run things. And, you know, you could put these in SBatch scripts if you're on a Slurm system in order to run this on a cluster, or we're going to run this all locally. Okay, so that was the bin directory, all your executables. Now we're going into 1B and looking at our data directory. This is where all of the information that you need for your simulations and for your inverse problem is going to live. Everything is controlled in a parameter file called par file. And then in order to run a simulation as well, you need a source and you need stations. You need something in order to trigger the seismic waves that you're going to try to record. And then you need locations at which you want to record those seismic waves to generate synthetic seismograms. And so they are named source and station. They have different names in the 3D code. In 3D Cartesian and globe, you can have CMT solutions. So taking, you can directly grab CMT solution files from GCMT, put them into SPECFEM. If you have, a favorite earthquake that you want to simulate, you can also do force solutions. If, for example, you wanted to simulate, I don't know, a hammer hit on the ground, you could have a vertical force hitting the ground. So there's flexibility in what kind of sources you can input in order to generate your seismic waves. If you run this code that starts with define print pretty, it's just kind of a look at these files, what they look like, how they're defined. So again, I said, yeah, we've got a data directory. This is also just what is packaged with the code with the initial example problem. We don't have a stations file in there yet. That'll get generated later. Here's just an example of what the par file looks like. It's just a text file with keys and values. I would highly recommend, if you start running SPECFEM on your own, to definitely just look at all the parameters. It's a pretty big file, and a lot of them are not actually relevant to every use case, but it is. There are some important ones. There's some interesting ones, and so I definitely recommend just reading through, getting an idea of what parameters control what parts of the simulation. Here you can see at the top, there's a title for the job, which is just used for labeling things. You can choose the number of processors that you want to run. Like I said, you're running distributed parallel problems. So you can choose how many processors, how many cores you want to distribute your problem to. Usually the more cores, the larger the simulation you're going to be running. And then things like controlling the time step. We'll talk about this, I think, later, but to make things numerically stable based on the problem that we're solving, we have to discretize time in a certain increment. And so you have control over that in the 2D and the Cartesian code. I won't go through the rest of the par file, but I'll leave that up for you to read. Here's the source file. This one is unique to SPECFEM 2D, but it has the same kind of components as you would see in 3D Globe. Essentially, what you need to do is define a location of that source. So in this case, since we're 2D, it's an X and a Z location. And then some kind of mechanism for that source to essentially initiate seismic waves. Like I said, you can use CMT solutions in the 3D code. And so you can see at the bottom here that there's actually a 2D moment tensor. Okay. In the par file, there's also an internal station definition. This is also unique to 2D. The idea for this internal is that you're defining lines. So you can see that in this part, we just want 11 receivers starting at some X and Z coordinate, going to some X and Z coordinate. But really in 3D cases and in kind of common use cases of SPECFEM, we're usually working from a stations file. And so this is just an example of what a stations file would look like. I think this is pulled in from a different example. And the idea is just that you have a station code, network code, location. In 2D, it's X and Z. And you can also put in burial and elevation if you have that information. Sometimes we just set it to 0. In the 3D codes, the coordinates would then be either lat lon, or if you're in Cartesian, then the X and Y of your Cartesian system. Output files, we run that cell. There's just the error message that we just got, but essentially everything, once you run a simulation, everything is getting dumped into output files. And so, if you run your MPI command and you're like, where are all my files? That's where you're looking.
That box.
Yeah. Okay. Now we're going to run the mesher. There's a built-in example problem in SPECFEM 2D. So once you compile the code, if you just run the binaries, it automatically knows to look for this example problem, and so that's what we're going to run. And I said I was going to talk about mesh and model. So just to give you kind of a really broad overview of what we mean when we say these words, here's an example of a mesh. This is a 2D mesh. This is Z is depth, X is horizontal distance. And you can see it looks like kind of a cross section with some topography. But what you can notice is that there's no value information to these cells. So the mesh really is just a numerical way, or it's a computational way of discretizing a domain of essentially turning the continuous world into something that we can run models on, something that we can run in a computer. Then when we talk about models, sorry, that's just another example of a mesh. This is in 3D Cartesian, so you can see it's a cube. The color on top is topography. This is from my work in New Zealand. I'm just showing you that we can have kind of complex topography on our meshes. We can also honor things like interface geometry, like Moho geometry, within the mesh. But again, there's no information about velocity structure or anything in this. If we look at the model, running that cell into A, the model is where we define our velocities. So here in the par file, there's a section for defining kind of model parameters. And this is just an explanation here. This is for a really simple layered half space case. And so you can see actually that this model definition has no information about spatial locations. It's just you're defining kind of quantities that are required for seismic wave propagation for, in this case, elastic seismic wave propagation. So you've got VP, VS, and density. And they're just defined as regions, so 1, 2, and 3, and 4. And then the idea is that when we run the mesher, we are assigning these parameters into different parts of the mesh. And so we're essentially building a model that has spatial and wave speed information. There are also more complex ways of inputting models that we're not going to go over, but you can also input things like tomography models, like external tomography models in the form of XYZ files. So if you've got a big text file that's got, XYZ coordinate and then seismic wave speed and density, you can input that in order to kind of, use somebody else's model for your simulations, or create your own custom model for input. But for the moment, we're just using this simple layered model.
How do you control the thickness layer? Like,
so that, in this case, that's happening in the mesh. So when this mesh is being created, it's each element is being assigned a region value. So you will see that in a later example, but kind of each cell there has a number 1, 2, 3, or 4, okay. And then the model values get assigned there. And sorry, the question was, how do you assign thickness to layers?
You have like different velocity, you have layers for a velocity there. So how do you define the thickness?
Yeah. So how do you define the thickness? And
you pick velocity, you run inside of the specific space. So basically, you only create the properties and then inside of those properties. So those velocity models have no spatial constraint. So you just say that, in my model, there is a velocity property like this. And then afterward, you define where that
Thanks, Felix. Yep, so we did model. And 2B is looking at mesh parameters. So actually, I should have just looked at this instead of trying to answer off the cuff. But here in 2D, in the parameter file, we're actually defining here the mesh. And so you can see we're saying we want it to start at some 0 coordinate and then go to 4,000 meters. We have boundary conditions. So in 2D and in 3D Cartesian, you can imagine, you harshly stop the mesh at some boundary because we can't mesh a continuous world, or it's very expensive to do so. And you can imagine when a seismic wave hits the boundary of a mesh, if you don't do anything with it, it's gonna see that as some kind of impervious boundary and it's gonna bounce off and reflect. And so you'll get some like artificial reflection. And so in a lot of our codes, we have absorbing boundary conditions or different types of ways of treating these waves so that they don't create kind of artificial reflections within our seismographs. I had a question. Sorry, which letter?
Fortran decimal D dot D naught.
Oh, the question was, what is the dot D naught? And that, yeah, that's a Fortran way of defining floats. Double precision values.
Something like a period.
Yeah.
I have removed the D and just left 0, and I have never had any problem.
Yeah, the question was, what is this D? And that's a Fortran kind of caveat. Felix is saying you can remove that and you'll be okay. Yeah. Yeah, neighbor is saying, yeah, if you don't include the D, then you might go to single precision. And so it's just giving you finer control over memory usage, over kind of accuracy of the numbers that you're using. Yeah, so that's an integer. Yeah, the question was, why is there no D on the NX? And that's because that's an integer, because that's just specifying the number of elements. So you can see here, you actually need to do a little bit of math because you have a distance and a number of elements. So you gotta, you do the division to figure out how big one element is. So I talked about absorbing boundary conditions. You can see here that the top is false. That allows us to have our free surface boundary condition. So we can have actual reflections off the surface, which is, for our case, physical. And then for your question, you can see here the regions that we're assigning at the bottom. So we want 5 different regions. And this is defining them by the element number. So you can see different layers here where we're taking spatial coordinates and we're assigning them some value of a region so that we will then assign velocity model values to. Yeah, and so you can do this in SPECFEM 3D Cartesian as well. This idea of kind of everything internal, generating your own velocity model based on kind of layers. But you can also, if you have more complex velocity models, you can also put them in using external tomography models. Okay. This is just to show you as well, interfaces you saw in this picture of the mesh that we had a topography in there. So we need to somehow define that as well. And so here you can see just a .dat file, just some way of defining a text file that tells us what the interfaces look like. Same in the 3D Cartesian code, you feed it some XY file that defines topography, XYZ file that defines topography. Here we've got 4 interfaces. So like I said, you can also define internal interfaces. So if you've got, let's say, like a MoHo model that you actually want to honor in your mesh, you want it to be a kind of a physical boundary in your mesh, you can input that there as well. And so you can just see X and Y coordinates defining kind of some undulations in the mesh. Oops. And then to determine, yeah, question? Yeah, the question was, do you have to define interfaces in a specific order? from bottom to top. And yes, yeah, it's kind of, it's baked into the code that it expects it in a specific order. And yep. Yes. Yeah, the question was, does it do a linear interpolation? So yeah, you can, it does do a linear interpolation. So you can have that discretized as fine as you want. Probably the safest thing is have it over discretized so that it, that the topography does not impose any kind of artificial like flat surfaces. You can have it over discretized and it'll downsample that as well. And yeah, you can see one example of this interpolation. If you just want like a flat layer, you don't have to define a flat layer. You can just define like corner points and it'll assume that it's just interpolating a flat layer there. So the question was, does the topography define the mesh geometry? Oh, they're hexahedrals. Yep. Cool. Okay. So we're moving on to 2C. Now we're getting ready to run SPECFEM. We're using size flows as a built-in tool to just manually edit the par file. You could also do this yourself. I mean, this is how probably everybody will start out, is you could just go into the text file with your favorite text editor and change it. But just in the interest of not losing people as we switch windows, we just have this built-in sempar command line command from size flows in order to change parameters. So we're going to run that. And you're going to see it's got some output where it tells you that it's just changing some parameters. So just to explain what those are, that's explained in that text box below. We're asking it to use the default model, which is what I just showed you, the internal parameter file definition. We're asking it to use 4 processors. So it's going to discretize, or it's going to distribute this domain into 4 separate chunks, which each get parsed out into a different processor to make things faster. We ask it to set up with a binary database, which just means that we wanted to output a specific file format after it creates the mesh, so that we can look at it afterwards. And then, yeah, we want to save the model in binary format. So SPECFEM, all the SPECFEMs have different ways of storing model information. The way that I typically use it is with kind of just Fortran binary files, but there are also different formats. I know Globe Code users sometimes use a format called Audios, but we're going to stick to the binary format for now. Okay, now we're running something. So if you run this cell block, this MPI run, hopefully you'll see an output log. We'll just see the top and bottom. There's a huge output log that comes out of this that kind of tells you all of the information of what's actually happening under the hood. But the idea is that we took that mesh and that model that we just saw in the previous cells, and we're actually creating it now. So they were just defined as parameters, and now we're actually creating the numerical mesh. So you can see that the output log comes out. We're running SPECFEM 2D, and it's telling us this is going to be a parallel simulation. If you run this code, this cell block, you can see that we're creating our stations file. So we're using that internal definition of stations, so it's just generating those stations, creating the stations file, which is like, again, the station code, network code, location. And then you can see these, excuse me, binary files, these database files, which actually just are the actual data representation of our model. So these are Fortran arrays that contain our mesh and model. And you can see that there's 4 of them because we've asked for 4 processors. And so our domain is actually distributed onto 4 separate files, and will be distributed onto 4 separate cores when we run our simulation. And then it creates a bunch of it creates a couple of VTK files. So VTK is the visualization toolkit. This is actually how we visualize our models. So if anybody's familiar with the program ParaView, there's other programs as well that can open these. In 2D, we can actually plot these directly with like Python, but when you get to large 3D domains, you can imagine it actually becomes its own problem in order to visualize, let's say, really highly sampled like global domains. So programs like ParaView are really efficient and feature-rich ways of visualizing things like your model. And these VTK files are one way of doing that. Okay, so we've all run the mesher. You're all experts at meshing now, and so now we're gonna go on to the solver. This is running SPECFEM 2D. And so the idea here is that, like I said, we had our mesh and our model. Now we're gonna input a force in there and let seismic waves propagate outwards. Here's just one example from my New Zealand work. You can see this GIF playing of a source being input in this domain of New Zealand, and seismic waves are propagating outwards. And on the right side, you can see that red trace is being drawn out. That's the synthetic waveform being recorded. And so you can imagine when you run SPECFEM 2D, 3D, what have you, this is what's going on under the hood. There's seismic waves are being propagated outward through your mesh and model and being synthetically recorded at whatever station locations you gave.
Can you show again the source? How it define the way where you define source, like what are the data that you have inside?
For this example,
For that example,
for the one that's playing,
yeah.
that was a CMT solution.
Okay.
So this is a 3D Cartesian simulation.
Okay.
But yeah, that was a CMT solution that came from a moment tensor inversion. Sorry, the question was, what was the
Like
source?
you give the moment tensor?
Yes.
Okay.
And it's not here anywhere. That was just an example
Okay.
to kind of
So
illustrate.
you can play a fixed component of the moment
Yeah.
tensor. Okay.
Yeah. Okay. So when we run this one,
Okay.
yeah, we can see, yeah, here we just had our receiver definitions again, and some information in the par file about how we want to save our seismograms. So this is also important. There are different ways of saving your synthetic seismograms. Probably the simplest way is a 2-column ASCII file that's just got time and amplitude, and you can choose what kind of information you want to be spitting out. So displacement, velocity, acceleration. Excuse me. So that's that seismotype here. There are a number of different quantities that you can output for your seismograms, and you can do different ones. You can mix and match.
Bryant, is there a way to output strain in SPECFEM?
Let's see. Question was, can you output strain in SPECFEM? Yes. Yes. In the global code, there might be different stages of development.
Thanks.
Yeah, I think people have worked on it. I don't know. Here in 2D, it doesn't look like strain is available, but I think in the 3D codes, yes. Good question. Okay, so we run that code block. We're actually running the solver. So we're taking that mesh and model. We're putting in that source that I showed kind of earlier at the top. And we're running the simulation for some finite amount of seismogram time that we've predefined. So hopefully that should be quick. This is a pretty small problem. And you can just see that, again, we're outputting a different log file from the solver this time, just showing you that things started. And then you can see at the bottom of that log message that things ran properly. And so, yeah, when you're running simulations, always just be, I'm always looking at the log files to make sure things are working appropriately. Question? Sampling rate? Yeah, the question was, did I define a sampling rate? Yes, yeah. So that was the end step and DT that I showed in the par file. Yeah, you have to define the time discretization that you're using. And this is partially based on how fine your mesh is discretized. There's a trade-off essentially of stability within your simulation. And so if you have a very finely discretized mesh, so you have really small elements because you want, say, high frequencies, you're going to need you're going to need a much smaller time step in order to keep the simulation stable. And the log files will give you suggestions on what the best values to use are.
I assume that it's likely that someone did this, they don't have the 4 processors, right? They're on computer, they need to change 4 by 2.
It should be, the question was, some people don't have 4 processors in the computer. It should be just kind of virtual, these like virtual cores.
Ah, okay, so even though it's going to work.
It should work, yeah, independent of your system. Okay. So just looking at the log file here, you can see that it's telling us what our mesh and model looks like. We've already looked over this. It's telling us how it's running through the time steps. So it'll update you every couple of time steps in the simulation or every predefined amount so that you can kind of monitor this log file to make sure your simulation is running. If anything happens, it'll throw an error message. And the bottom, you can see that because we asked it to output the model files, it's given us these bin files, saved them in the data directory. So we're going to use that to visualize our mesh model. Okay, final stretch here. We're looking at the output files. So you can see, again, like I said, things are being stored in these binary formats. And we want to look at them. Usually, you don't really want to just like run simulations and not know what's happening. You want to know what your domain looks like. And so if you run this cell, this is just a Python code block that takes those binary files, reads them in with some Python, plots them up, and then also plots information about the interfaces, et cetera. And this is all kind of information that's combed from the parameter file, from the interface file, from the sources and stations, just so that we have a clean representation of what we just did. So here you can see our domain. You can see it looks like the same as the mesh that I showed earlier. You can see the topography, but now we've got the model values actually assigned. And then the locations of the sort stations, which were input through the parameter file, and that source is that yellow star at depth. I'm gonna skip through these, and then, yeah, this code block was just to, again, try to link those interfaces that we put in. You can, if you like, put the numbers in from this interface file, they would follow the geometries that you're seeing separating these materials. And now, probably what everybody cares about is the waveform. So we had a bunch of stations, we had a source come out, we had waves propagate outwards. And so we should have some synthetic waveforms that explain the motion that these points in the model recorded. And so we're looking at these waveforms. They've been outputted as 2-column ASCII files within the output files directory, labeled by their network, station, and component. And the D here at the end of SCMD just signifies that they're displacement waveforms. Here's just an example of what that looks like. Like I said, time on the left column, amplitude on the right. Since this is the beginning of the simulation, I'm showing it's all zeros because there's no arrivals yet. Then we could plot that. Since it's just a ASCII file, you could plot that with whatever you want, NumPy, OpsPy. Here, just reading it in with NumPy and plotting it with Matplotlib. So you can see some arrivals coming in from that source. SciFlows has some built-in plotting tools to do the same thing. It reads it in as an OpsPy stream object, plots it out. Same thing. And then, like I mentioned earlier, the tool PySep that we have has a built-in record section plotter. This is just a brief introduction to that. If you run that, it's a command line tool, or you can use it in Python. It'll read in all of the seismograms that got output and create a record section for you. There's options for sorting things by distance, by azimuth. You have some control over what the figure looks like. So if you run that code block, it's giving you lots of log messages. it worked. Cool. Oops. It's a little bit big to show on the screen. You can just see the record section there. I think this is sorted by distance, so you can kind of just see the move out of some of these phases coming out. Yeah, pretty cool. And the nice thing about SPECFEM 2D, which is not in the 3D or globe codes, is that natively SPECFEM 2D will output wave field snapshots. So we can actually see the wave field propagating outwards. In the 3D codes, there are options to output movies of the wave field, either at the surface or through the volume. So if you're interested in seeing the kind of, if you've seen movies of people running SPECFEM simulations of like wave fields propagating through basins, for example, those are natively out. Those can be output by the 3D and globe codes. Yeah, so these are, again, the parameters that control that. We want to tell it how often we want to output an image within our movie. You can imagine if you're trying to output every time step at 0.011 seconds, it's going to be a lot of files. It's going to be pretty big. So there's just some granular control there. And then these are just, in SPECFEM 2D, these are just output as JPEG files. So we're just opening these, and I think this is the end of this first notebook. We can just see these wave field snapshots showing us the simulation we just ran. So these are at different time steps. This is kind of early onset of the source. You can see waves propagating outwards, starting to hit that top boundary, starting to hit some of these layers. A little bit later, you can see some reflections off the top surface. You can see wave fields being modulated as they go into a different material, that light gray box there. I think that's supposed to be a cavity, maybe. And then at the end, you can see things get really crazy. Wave fields are bouncing all over the place. You can see the absorbing boundary conditions on the right-hand side working. You can see waves are actually dissipating outwards and not being reflected back into the domain. And I think this is a good illustration of why we use tools like SPECFEM. The wave field is crazy when you're in a complex domain, and you need to honor essentially the full physics of the wave equation in order to understand all of the phases that we're seeing, all of the shaking that we see in our seismograms. And so tools like SPECFEM that actually allow you to honor a lot of the complexity and the full physics of the problem are super powerful for answering science.
All right, maybe that's good on the fly question. What's that? The box domain.
Yeah. Question is, what is this box domain? Cool. Maybe that's a good point. That's the end of that first notebook. The next notebook will be going into running our own Ford simulation, so not doing the example problem, but actually setting it up on our own. And then there's an exercise at the end. So hopefully you paid attention. There's it's going to ask you to change some of the parameters, set up your own problem. But maybe we'll pause there, have a short coffee break, time for questions, let's say 10 minutes, and then we can resume with notebook 2 after that. I had a question over there. A dozen on in 2D, yeah. You can do 2.5D. So I think there are some cases where you can do like 2D planes and I think like interpolate between them. But yeah, it is just solving on this 2D plane. Yeah, sorry, the question was, what does 2D do with the third dimension? And it does not honor the third dimension. yeah, maybe some homework in this break period is, can you figure out what the material is in that small white domain here? It was defined somewhere. We did look at it at least at the information. So let's take 10 minutes. You got any questions? Feel free to raise your hand. Yeah. Sure. Yeah.
The font file to only define, as far as I remember, 3 moments of elements. So I was wondering what happened to the others. I mean, for instance, in the CMD solution file, you put the others as 0, but you need to specify the 6 elements. In this case, you only specify 3.
There's only 3 because we're just solving in 2D. Mhm. Yeah, the question was what happens to the other 3 moment tensor elements, and they don't exist in 2D.
Thank
you. Sure. Coffee break, 10 minutes, and then we'll resume with notebook 2.
The output directory, Bryant, when you enter files between the local computer and
Should be, let me just move.
what I remember in Docker, it should be not an output directory or something like that, but I can find it out in the
All right, everybody on Zoom, we're just about to get started again. All right. Thanks for sticking with me. So we're going to notebook 2 now. And the idea here is that we are going to take another one of the example problems and set it up. And then we're going to give you some time for an exercise at the end where you kind of modify this problem in order to get a feel for how to actually like maybe start working your own research problems. We're going to notebook 2, which is just at the bottom here. I've already got it open. Same startup things. If you forgot in the break how to run Jupyter Notebooks, there's some quick tips there. But we're going to start in section 1. And this is a little bit of, I guess, a personal touch on how I run SPECFEM. What you could do is clone SPECFEM and run your simulations directly in that clone repository. And then if you wanted to run a new problem, you could clone it again and run in a new repository. That starts to get kind of cumbersome. You've got a lot of SPECFEM 2 directories you've just installed. And so something that I would recommend is that really all you need to run a simulation is your bin directory that's got your executables, your data directory, which tells you where your sources and stations are, your par files in there, and then output files. So what I like to do is just create a separate working directory that has those 3 subdirectories, and then I run problems in there. So that's just what this first setup does in these first 2 code blocks. Just importing some stuff we need, and then creating this empty working directory and filling it up. So we're symlinking in the executables. We're copying in a data directory that's already got some files ready from an example problem. And then we're making an empty output directory file. One thing I wanted to mention, because I got a couple of questions during the break, is that all the stuff we did in the previous notebook actually is not saved on your local machine. That was just saved directly into the containers SPECFEM 2D directory. But all the stuff we're doing in this notebook will be saved local. So you'll be able to find it in that local directory you made earlier. Okay, so we're in this working directory. It's called SPECFEM 2D work directory. We've got the 3 requisite subdirectories we need: executables, data, output files. We've got Carl Tapin here, who created this example problem in 2007. We're going to explore it a little bit. It's a 2D checkerboard forward simulation. And so we've pulled in the data directory from this example problem. It just lives in the SPECFEM 2D repository. And you can see we've got all of our favorite files in there. We've got a couple different parameter files for different use cases. We've got a number of different sources. So you can see that each source is individually defined in its own file. So this is analogous to, let's say you're doing a 3D simulation and you want to simulate like 100 earthquakes. You're going to need 100 different CMT solution files to define each of those events. And then we've got a stations file. So we run the next one. We can have a look at the velocity model. And here you can just see, again, there's only one line there. So we're really defining one material property. So we're looking at a homogeneous a homogeneous 2D plane case. And that command at the bottom was just show that, again, we can use size flows in order to look at the parameters. And we can also use it to change the parameters of the velocity model. So keep that in mind for the exercises later, that you could do that either with size flows or you could do that by hand. Yeah, so we're just looking at the velocity model. You can see, again, we're looking at a different part of the parameter file that's defining our mesh. In this case, since we're in 2D, you can choose which plane you're looking at. So in the first notebook, we were looking at the XZ plane. We're looking at essentially depth slices, depth cross sections. But you could also think about things in the XY plane. So if you wanted to just maybe do surface waves or what we call membrane waves, you can solve problems essentially on this XY 2D plane. So that's what this problem is going to be. It's going to be the horizontal plane. You can see that, we go from 0 to 480 meters, 480 kilometers in this domain. And we've got absorbing boundaries on all sides because now we don't have a free surface. We've got essentially like a surface plane. And so we want the waves to be absorbed on all the boundaries. And then interfaces, you can see there's no topography since the interface is defined like edge topographies or internal topographies. We don't really want topography on our XY plane. And so we just have a big flat layer. We're just going to plot that just so we know what it looks like. That's what that next code block looks like. Here, I'm just taking information from the parameter file, plotting it there, just showing you what I've been talking about. This is an XY plane with some amount of dimensions. Each of those little cells represents its own spectral element, and it's a homogeneous case. So everything is 3.5 kilometers per second wave speed. We looked earlier and we saw we had a stations file and a bunch of source files. So just plotting those so we have a general understanding of what this looks like. I think this is Southern California. But you can see we just got a bunch of stars, which represent our earthquakes, and a bunch of blue triangles, which represent our stations. And so these were defined in the file. So we've seen that before. The next code blocks just plot those in isolation with some numbers, excuse me. So that when we're doing the exercise later, you can come back to these for reference if you want to, let's say, pick one of those sources as your test case, or you want to pick some subset of stations. And so that's a little bit messy, but it just gives you an idea of what that distribution looks like. Yeah, so we've got everything we need to run a simulation. Source, stations, parameter file, things are set up. What we need to do is choose one of those sources to run for our simulation. We can't run them all at this, well, we can run them all at the same time, but then all those wave fields start to interact, and synthetics don't probably represent anything that we care about. And so we want to run simulations one at a time. So in this case, we're just picking a single source, picking source 1 in order to run our simulation. And we are just making sure that, well, in this case, we're picking one station. And so SPECFEM is looking for specific file names, so stations and source. And so just to reiterate, this case is single station, single source. We want to just set up the parameter file with this code block, which is, again, telling it 4 processors and to use the stations file rather than the internal definition of stations in the parameter file. And then we're going to run. So we're doing the same thing we did in notebook 1, but we've got one source, one station, and we're running simulation through that homogeneous domain in the XY plane. We've run both the mesher and the solver in the same code block. So by the end of that, once it finishes, you should have a seismogram, synthetic seismogram. And you can see that in 3E. I'm kind of blasting through since we've kind of seen all this before in notebook 1, but like we've seen before, we've got our database files, one seismogram because we've only got a single station. Got those VTK files for visualization. We've got some wave field simulations as figures as JPEGs. And we can look at that waveform like that, a nice clean arrival. And we can look at some of those wave field simulations. And you can see smaller. It's the beginning. There's the initial input of the source, waves propagating outwards through this homogeneous medium, and then further out, and they've gone past the station now, so Now the station is recording synthetics. Okay. So since you're all experts at SPECFEM, I'm going to throw you into an exercise. All the instructions are there from section 4 onwards, but I'll just go through them so that we're all kind of on the same page. What I'm going to ask you to do is mess with the model, play around with it. At the kind of least case, you can, change, like perturb some of the velocities. Going to ask you to define your own stations file. You can be kind of creative with this. You can try to, generate an array if you want. You can take some subset of the stations file that's in there. You can create whatever crazy geometry you want. I'm going to ask you to pick a different source and maybe play around with the source parameters. If there's moment tensor components in there, you can look through that source file. There's different types of source time functions and different types of source implementations. So play around with that. And then we have all the requisite parts. And so rerunning the mesher and the solver and looking at your results and seeing what kind of crazy things you can come up with. So this code block at the top is just a setup. Just creates this empty exercise directory that all of your work will go into, make sure that all of the correct files are in there and puts you in that correct directory. And so all the tasks are here as I described, and ask you to do things like edit the model, source and station file. For those who are comfortable working in Jupyter Notebooks in the cells, you can, you can look at things through commands, like with the magic commands, you can look at ls and see, you can edit your files directly through that. Or if you're more comfortable, and you want to do, if you're more comfortable with doing things manually, you can click this directory button here and go to work and exercise 1. That's work and then exercise 1, and then that's the working directory you're in. So let's say you wanted to modify your source file. You can see all the sources here. You can just double click and that'll open it up in a text editor, and you can play around with all those numbers. And unofficial prize for whoever gets the craziest seismograms. Yeah, so I'll probably give like half an hour, play around with that. We'll have people walking around if people need help. Feel free to raise your hand. And yeah, on Zoom as well. We'll play around with that exercise and see what you can get. Thanks.
Would I just do like some more on plan?
Just one announcement. I've had a couple of questions about how do you use size flows to edit the velocity model? So there's, probably should have put that in instructions, but if you use the sempar command and then you put in the parameter name velocity model like that, it'll tell you what the model parameters are. And then if you copy that whole string and put it in quotes, you can modify these values like that with the same command and modify your velocity model. So just if you wanted to do that directly from the notebook, you could.
question, we didn't know, that's a bit better. It's better than first one. Yeah, actually, so.
I'll probably give everybody maybe like 10 more minutes for the exercise, just in the interest of time, and then we'll move on to a different notebook. But just wanted to, for those who are maybe stuck or wanted to see one way of doing this, probably maybe some of you have already seen it, but there's solutions. So in that same directory, there's a exercise solutions directory, and so there's one for notebook 2, where I've kind of pre-filled out some of this stuff and done my own form of this. So if you were stuck, you wanted to figure out how to get past something to help you continue with exercises, or afterwards, if you wanted to kind of do this on your own, the solutions are there for you.
So, you have this recently? Because I grabbed the container yesterday, and I didn't find that.
It should have been sometime yesterday,
Okay.
like
That's okay.
afternoon yesterday.
That's
But if you git pull from the repository, you could also grab it.
38. Why do you use SEMPAT for writing a station file?
Sorry, Zoom, I was muted. Yeah, there are probably too many notebooks in the directory to get through today. I think what I'm going to do is do notebook 3, which is an introduction to adjoint simulations. So this is the idea of building up for inversions when we're trying to update structural models using essentially seismic data. I'm going to give you a little primer for that, and that sets you up nicely for the SPECFEM 3D globe tutorials coming up tomorrow as well. Maybe just before I jump into that, I will go over what the other notebooks are in the directory. There's a notebook 4 is an intro to SPECFEM 3D. It does essentially the same things. Still. I think I'm okay now. So yeah, notebook 4 is intro to SPECFEM 3D. It kind of does the same things, just does a bit of walkthrough of the directory, shows you the files and tells you kind of the differences between 2D and 3D, so that if you wanted to explore 3D Cartesian, you kind of understood the differences between what you just learned today and what is required in 3D. There's not too many. And then the notebook 5 is an intro to size flows, which is that workflow tool I talked about. The idea there is that now you know how to run the forward problem, kind of in 2D with examples. And so the idea behind size flows is once you can solve your forward problem in a way that you think is valid and stable, you can plug that into this automated tool, and it'll run the inverse problem for you. It'll do essentially adjoint tomography and model updates. And it's compatible with SPECFEM 2D, 3D, and 3D globe. So that notebook essentially does an automated forward problem with something like 10 sources. And then the exercise asks you to modify that in order to run an inversion and do model updates. But it's a little bit push button besides the exercise. So I think maybe what's most illustrative is going through some kernel generation, so you understand kind of the procedures that we go through when we're running and doing adjoint tomography. Okay, I'm in notebook 3. This kernels and adjoint simulation. And the motivation here for those who are unfamiliar with adjoint tomography is that we can use essentially the tools that we've developed here, this spectral element solver, in order to solve an inverse problem, in order to do structural inversions. So this is a figure from Carl's paper in 2007, kind of just showing you graphically what we mean here is that we can solve the forward problem. That's that left column where we're propagating a wave field outwards. We've been seeing wave field images from our SPECFEM 2D simulations. That's the same idea. Now we have a synthetic waveform. And if it's a kind of a realistic case, we should maybe also have some data, a real waveform that the synthetic situation is trying to mimic. So in this case, Southern California, there's an earthquake that's happening on the border and it's propagating outwards to some station in Southern California. So there's real data from that earthquake. And the idea is that the synthetic and the data may or may not look the same. And if they don't look the same, then we're making some errors in the way that we're either approximating the structure, so how we're defining the velocity model, or the source. In this case, we're assuming the source is correct, and so there are differences between data and synthetic that we're attributing to essentially errors in the way that our model is defining or approximating real Earth. And by solving what we call using the adjoint state method, which I'm not going to go into math or terminology or detail, the idea is that we can take the misfit between those two waveforms and essentially propagate that backwards through another simulation in order to get an idea of where in our model this misfit, the differences between the data and synthetic are coming from. So that's the second column, is the adjoint simulation, where we're essentially sending misfit information backwards through a simulation, and then we're interacting that with our forward wave field and creating a kernel. So the kernel essentially is a volumetric quantity that tells us where in our model we can change values in order to affect the misfit. So what we're trying to do is fit the waveforms. We're trying to move our synthetics in order to fit them to our data by perturbing our model. So this whole notebook is essentially showing you technically how we actually run these adjoint simulations and generate these kernels. Okay. So we're gonna, same setup, import a bunch of stuff that's gonna help us look at waveform models. And then we're creating a new working directory just so that we have everything stored. And we're using the same experimental setup we just saw in the last notebook. So all those sources and stations I showed, and we're going to use that same kind of geometry and setup. Looking at, in 2B, looking at that half space again. So that'll be our starting model. And in this case, we're not using actual seismic data, but we're going to do a synthetic inversion. So we're going to create two sets of synthetics, one through this homogeneous model, another one through a checkerboard model. We're going to use the checkerboard as data. So we do this a lot in seismic tomography in order to test methods, in order to understand if our source receiver geometry is working out for us. Is that rather than using real data, which can be noisy and difficult to work with, we have well-behaved synthetics that we generate from a known target model, from a known known target model, and we try to use our inversion tools to get to that target model. So in 2B, we're just showing that, excuse me, checkerboard model. This is a good explanation of the external tomography models. So it's looking at this already predefined text file, which has index on the left column, and then X and Y coordinates, and then 3 columns to define what the model values are. So that's density, VP, VS. And so a lot of the kind of external tomography models, maybe you've got a model of whatever region you're interested in. This is one way of inputting a model into SPECFEM for your simulations. We could plot that since it's just a text file. So this code block just goes through, reads in those files and plots them so you can see the checkerboard. So it's the same domain. I think the central value is the same as the homogeneous case, and then you can see that there's some kind of perturbation, I think maybe plus or minus some percentage of the initial model. These are just kind of repeating well-behaved patterns that we can look for when we are generating our kernels to see that things are working. That was for VP, and this is for VS. They look the same, just different parameters, different velocities. And then, yeah, just to understand the color scheme here, red colors means slower than the average, blue colors mean faster than the average. Like I said, we're using the same geometry that we saw in the previous notebook. So all of those sources as the yellow stars, all of the receivers as the blue triangles, and then just plotting sources and stations over the top, just so you have an idea of what those look like. But for this specific case, just to keep things simple, we're gonna have just one source, one receiver. Okay. So let's say you've run your forward simulation, you've got a synthetic. Now we want to set up the adjoint simulation. The idea is that in this new simulation, we have essentially the misfit being propagated outwards as a wave field, and it's interacting with that forward wave field, like in this image. So we're going to 3A. And first we need to generate our synthetic data. So the idea behind this code block is just that we're running a forward simulation through that checkerboard model and generating synthetic seismograms, which we can then use as our quote unquote data. Just to talk through what's going on there, we're taking one of the sources. We're using all of those stations I showed earlier. We're using the parameter file that defines the checkerboard model in order to define our model parameters. And then we're just running MESHFEM and SPECFEM. And then now we've got a bunch of synthetic seismograms, which we will use as our data. And if we look at one of those waveforms, you can just see it looks like a standard synthetic waveform. Okay, so we've done the same thing that we did before. We ran a forward simulation. We've got essentially a set of synthetic seismograms that we can use as our data. And so now we need to set up the actual simulation that we're doing. So we've got we're going to our starting model, which is our homogeneous case. And doing the exact same thing. This code block is essentially taking the homogeneous case, setting it up with the correct parameters, and then running MESHFEM and SPECFEM to generate synthetics through the homogeneous case. And one point I want to make here is that there's a parameter in the par file called save forward. And the idea is that in the adjoint simulation, we need to backpropagate the forward wave field in order to interact with the adjoint wave field. And so we need essentially to store information at the end of the simulation that tells us what the forward wave field was doing, so that in the adjoint simulation, it can get backpropagated. And so just, if you're going through the kernel simulations, just make sure that when you're running your forward simulation, you're saving the forward arrays. So now we can see that when we diff the two different files, so we've got a set of output files from our data creation through the target model. We've got a set of output files from our synthetic creation through the homogeneous model. And the only difference there was that the model diff changed and that we saved the forward arrays in the homogeneous case. And so those are the files there. If we look at waveforms, waveforms look like synthetic waveforms. And we can see that, yeah, 2-column ASCII file. Okay, so that was kind of all. We've already seen all that stuff. We're just kind of setting up the case where now we've got data and synthetics. Now we actually need to do our adjoint simulation. And so what do we need for that? We need adjoint sources, which are essentially waveforms that quantify the misfit between the data and synthetics. So that's what we're going to do in section 3C, is essentially define these adjoint sources, the misfit between data and synthetic. So that first code block is just plotting synthetics, the data and the synthetics. So the typical color scheme is red for synthetics, black for data. So you can see that there's some time shift that's been introduced by the perturbations that we put into the checkerboard model. So that's a quantifiable difference between them. So we can use that information to inform the adjoint simulation. If we zoom in, we can just see that there's some few seconds time shift between the two. A big question in seismotomography is, misfit functions. How do we actually define the misfit? There are a lot of different ways, a lot of different techniques for doing so, and each of them gives you different kind of sensitivities to different parts of the waveforms, different phases. Probably one of the simplest ones is the waveform misfit function, which is just taking the direct difference between the synthetics and data. So that's what we're going to do here. It's just essentially doing a waveform difference between those two. And there's an equation there in 4a telling you what the misfit function, how it's defined. And then if we plot that, you can see that now we've got this time-dependent green waveform that is telling us essentially the waveform differences between the synthetics in red and the data in black. That's what SPECFEM needs for the adjoint simulation. So you can imagine if you've got multiple stations in your simulation, and each of them, let's say, is 2-component or 2-component in 2D, 3-component in 3D. You will need adjoint sources for each of those. So you're going to have essentially the same amount of adjoint sources that you do for synthetics. And those just need to live in a certain directory that I'm going to show you here. So yeah, we've got our forward arrays, we've got our adjoint sources. So we're ready to run an adjoint simulation. Those are the 2 components you need. So just going back into my directory, and the adjoint sources need to live in just a hard-coded directory name called SEM, which is for spectral element method. They have to have some kind of specific naming scheme, which is explained here, but it's kind of all just technical details. So, there are tools out there to help you to make adjoint sources, or you can do it yourself if you define your own misfit function. Just the idea is that when you're running your adjoint simulation, you just need all the correct adjoint sources. So we've got everything ready. And so the only thing we need to change is the simulation type in the parameter file from 1, which is forward simulations, to 3, which is adjoint simulations. And here we're just telling it to save those kernels as ASCII files so we can look at them later. We're using the same executable, but with the simulation type set to 3, now SPECFEM knows it's running an adjoint simulation. If you, let's say, didn't have the correct adjoint sources, it would throw an error. If you hadn't saved the forward arrays, it would throw an error. So you would, if you try to do this in a research capacity, it's kind of just trial and error until SPECFEM is happy with you that it has all the correct files. Yeah, and so what it's doing in the background is, if you think back to that image that I showed earlier, it is time reversing the forward wave field, propagating outward the adjoint wave field, and generating essentially the interaction between the two as some volumetric quantity. Okay, so we've all run an adjoint simulation. So the outputs of that adjoint simulation are going to be kernel files. The idea is that this is a volumetric quantity that's telling you where in the model you can make changes in order to affect the data synthetic misfit. So this code block is just showing you we're moving some of those output files into the correct directory just so that we can plot them. And then if we use this plotting function, which is in size flows, you can see that we've generated a kernel. And yeah, this looks like the kernel that we saw in the figure before. You can see the source and the receiver there, and you can see essentially what it's telling us is that where the colored regions are, if you perturb some velocities there, you can have some effect on essentially that aesthetic trace, that red trace that we saw earlier.
So these are sensitivity kernels, Bryant?
Yes, these are misfit kernels because they have some information about the data in there. So they're different from like banana donut kernels, which kind of just tell you, sorry, the question was, are these sensitivity kernels? And the kind of nomenclature here is that we call these misfit kernels because they contain some information about the data that we're using. They're not just showing us kind of the sensitivity of the specific phases that we're looking at, but rather information about the actual data synthetic misfit. Yeah, and similar to the forward simulations, SPECFEM generates images for the adjoint simulations. So you can see here, this is the same kind of setup that we saw earlier, but now the wave field is propagating outwards from the receiver. And so this is that kind of misfit information is being propagated outwards. That orange cross at the bottom is the source. And you can see at some point later, propagates outwards. And so if we think back to this image all the way over here, this is what's happening. This adjoint wave field is being propagated outwards and is interacting with the forward wave field in order to generate this kernel we just saw. Okay. Yeah, and in this case, this kernel looks pretty smooth. It looks pretty well behaved. It looks kind of like a really nice kernel. But sometimes that's not the case. Especially, when you run an adjoint simulation, we're fortunate enough that we can do just one adjoint simulation per event. So if you had, not just one station in here, but you had the whole spectrum of stations that I showed earlier, each of those would have an adjoint source, and each of those would be propagated in the same adjoint simulation. So things get really crazy, and your kernel becomes this whole entire summation of all of the misfit information interacting with one another for a given source. And sometimes that looks pretty crazy. Sometimes there are some kind of numerical artifacts that crop up. And so a lot of the times in tomography, we need to do some kind of regularization in order to make these things a little bit more well-behaved. So I talked about earlier in the first notebook, this idea of smoothing or regularization. And so just at the bottom, I'm showing you one last code block. We're actually running the smoothing code. We're telling it that we want to smooth by, we're essentially smoothing by convolving with a Gaussian that has some spatial width. And we're smoothing that kernel quantity. And now you can see we took that kernel that we had and we convolved it with a 2D Gaussian that has some finite width. You can see things are a little bit more, the colors have blended a little bit more together, and our kernel is a little bit smoother. So this is kind of a normal thing that we do in adjoint tomography, is that we tend to regularize or smooth our kernels before adding them back to our model. Yeah, and so I don't show it in this notebook, but the idea for the inversion now is that now you've got this quantity that tells you how to change your model. So you can add that back to your starting model and rerun your forward simulations. And now you've got synthetics that have some introduced time shift because you've changed your starting model. And hopefully the kernel informed it correctly that now that time shift is a lot smaller than the initial one. And then that's the inverse problem, is now we've got an update to our structural model. We can run this iteratively in order to better fit the data to the synthetics. Okay, that was the end of that notebook. I think probably in the interest of time, I'm not going to go through the other notebooks. But maybe we can open it up for any questions or discussion. We've got about 20 minutes till lunch, so any question? Yeah, the question was, can you resolve for attenuation? Yeah, I mean, technically you can invert for attenuation, but you would need to find a misfit function that is essentially sensitive to attenuation structure. So if you do, that'd be really interesting. I don't know if I've seen people do attenuation tomography.
So maybe tomorrow I can talk.
Yeah.
But it just needs to change the difference of such a result.
Yeah, so Avery, for those on Zoom, Avery was just saying that you need adjoint sources that are sensitive to attenuation structure, and she's going to show some of that tomorrow. Questions about what we saw today? technical details.
So say you had a model that maybe you had as like an umpire array. What would be the process to get that model into SPECFEM?
Mhm. Question was, if you had a model as a NumPy array, how would you get that into SPECFEM? So yeah, what we saw in 2 was, oh no, sorry. We saw here was this external tomography model. This text file. So probably one of the easiest ways is to, yeah, write essentially a text file that's formatted in a way that SPECFEM can read it, that has spatial and property information. And it doesn't have to be the same discretization as your mesh. Could be more finely discretized and then it'll be downsampled, or it could be coarser and then it'll be interpolated.
How long does the size of those notebook take to run?
Maybe like, I could probably fill the time with that.
Thinking to launch it.
Sure.
Sure.
Yeah. All right. Yeah, I probably got 20 minutes, so I could do size flows. This is another kind of push button one, but there's exercises at the end, so maybe at that. If I get through this quickly, we can fill the time with that. So size flows, again, is this automated workflow tool. As you've seen, there's a lot of kind of manual steps required to run a simulation. And let's say you've got like some number of earthquakes. It's a lot of bookkeeping, a lot of manual tasks in order to run, let's say, like 100 forward simulations. So the idea behind something like size flows is that it just automates that procedure to make things a little bit easier, especially when you get to really large problems. There's a potential to introduce, user error if you're manually updating a bunch of CMT solutions or parameter files. And if you've got computational hours on the line there, you don't want to waste time or waste resources accidentally making a mistake. And so that's kind of the motivation for creating tools like size flows. So we're going into notebook 5, and here is a nice workflow image just to kind of give you an idea of the problem that we're trying to solve here. So you can see at the top left, this is the forward problem. We've got some model that we want to input. We want to generate synthetics. So we make some guess, we create a starting model, and then we generate some synthetics with our forward simulation. And then what I just showed you is that then you've got some data, which describes the real case, the real situation that your synthetics are trying to mimic. And you do some kind of misfit quantification, you figure out what the differences are between the data and synthetic, and you generate those adjoint sources that we just saw in the previous notebook. And then you feed those into the adjoint simulation and you get your kernels. And when you do this for lots of different source receiver paths simultaneously, then you can sum those up and you create essentially the gradient of your misfit function, which tells you how am I supposed to change my model to better fit the data and synthetics. And then we do this iteratively because we can't essentially jump to the final model in one go. And so we keep updating our model in small increments, keep improving our waveforms until we hit some kind of criteria which tells us, hey, we're done with the inversion, or we cannot fit these waveforms any better. And so the idea behind this is that size flows tries to handle the automation of this kind of workflow. It is a Python-based tool. It's mostly supposed to be run from the command line, and similar to SPECFEM, it's got a parameter file. So if you run that first code block, you can just see that there's a help message, and there's a number of different functions that we can use to help us run an inversion. And then in section 1, what we're going to do is essentially automate the forward problem that we just ran. So importing some stuff, SciFlows is already installed in the con environment on this notebook or in this container. So we can just directly run it. And it's got some built-in examples. So if you are able to install it correctly through your conda environment into a conda environment, it's got this examples function. So there's some built-in examples so that you can just kind of run something with SPECFEM 2D and then explore it a little bit and then modify it for your own research problems. So we're running example 3, which is just automating the number of forward simulations. And so you can see what it's doing in the background, and this setup is essentially what we've been doing in all these notebooks is like generating some synthetic data to use, setting up the correct working directories, kind of making sure everything's in the right place. And there are going to be some number, 10 sources, 25 stations, so 250 waveforms. If you had run that code block successfully, this is just exploring what it's set up. Same things we've been seeing, some working directory that's got an initial model and target model. And then this is just an exploration of the parameter file. It's in YAML format, which is, again, just another text-based format. And you can see it's got doc strings in there to explain what's going on. The way that SciFlows works is it's kind of modular. And so you can essentially plug in like different workflows. If you wanted to just do forward problem, you could do that. If you wanted to solve the inverse problem, you could do that. It has built-in ways of interacting with systems. So you can run directly on your workstation or your laptop. But with the same parameter file, you can also put it onto a cluster. I've run it on a number of different clusters. It works with a couple of different job schedulers. And it's kind of built on this inheritance structure so that if you, the modification required to run it on your own clusters is pretty template style. Here's just the parameters that we're looking at for the forward problem. It has some form of like checkpointing. Let's say you're running the inverse problem and you want to stop after it runs the forward simulations and look at your synthetics, make sure things are working. You have the option to do that. And then there are some parameters for the solver. You can see things like the smoothing parameters, which I showed in the last notebook. You can smooth kernels automatically. It has kind of wrappers for all these SPECFEM functions. So the idea is really that you set up the forward problem, and then you give that to SciFlows, and then all you're doing is working with SciFlows after that. It takes information from the data directory in SPECFEM. So here we're just giving it all those sources that I was showing in the other notebooks, and just saying, hey, use these in the forward simulation. And here we're just asking for 10 of them. So ntask equals 10. I'm saying look for all these files called source and just pull those from the data directory, run simulations with that. And then finally, just needs some paths. You need to tell it, where's my SPECFEM binaries, the executables. If you have data, just telling it where the data is, and it kind of requires its own separate formatting directory structure. And then where is the SPECFEM data? Where are the source files, the station file, the parameter file? It reads from all that in order to understand how to run its own simulations. Yeah, I'm going to skip over 1D. This is just the idea is that like, this was also for the exercise. Let's say you did a bunch of automated forward simulations. If you then wanted to run the inverse problem, you'd have to essentially create a new parameter file, because the parameter file is created dynamically based on what kind of problem you're running. And so there's just some tools in there to make that a little bit easier. So if we do 1E, if everybody's at the same place and we just run that, essentially everything has been set up by the example setup, and what's going on, I'll just kind of walk through as it is outputting this log file. So it's doing some setup, and then it's going to essentially create 10 different SPECFEM working directories and run the forward simulation in all of them. I think it's going to do that. It's going to do that in serial because I'm just on a laptop. But let's say you're on a cluster. in that case, it would distribute this into like 10 different jobs on the compute nodes and have all those run in parallel. And it's got some job scheduler monitor, so it watches those jobs, makes sure that they're running. If all of them complete successfully, it'll move on to the next step of running the adjoint simulations. If one of them fails, it has the ability to monitor that and rerun that failed job to see if it was just like a system error. And has some nice checkpointing features. Let's say a forward simulation fails. You could just rerun the workflow and it would try to rerun that simulation. Yeah, you can see the log messages here. It's going through serially. It's telling me what my model parameters are just as a check. And then it's going through for each of the sources that I wanted and running the forward simulation. So it's just running those executables that we were looking at earlier. Since we're just doing the forward problem, it stops there. If we were running an inverse problem, it would keep going, quantify misfit, generate adjoint sources, run your adjoint simulations. And just a tour around what it looks like so that you're kind of familiar if you decided you wanted to use this tool. This is the kind of standard size flows working directory, is that it's got a scratch directory where everything is happening. It's got logs. So if you're on like on a cluster, each of the individual simulations you're running is actually it's self-producing log files, and so all of these are getting saved in separate files and they're being organized. It's got its own master log, which we just saw, and there's the parameter file. And if we look at, what is this? Yeah, and if you're running like inverse problems, it's also, as it's updating a model, it's storing those somewhere where they can't get, where they're outside of the scratch directory. And this is maybe just to illustrate that it kind of takes care of all of these bookkeeping and processing tasks that you would have to either manually do yourself or write a bunch of Bash or Python scripts in order to do. And then I'm going to skip over that and just in your own time, if you're interested, this exercise essentially runs through taking that forward problem that we just set up and converting it into an inverse problem in order to do a model update. So it's asking you to essentially set up the required files, directory structures, and modify the parameter file of size flows in order to run the inverse problem. Excuse me, run the inverse problem. Cool. I think I'm going to stop it there. And maybe one last thing to point out is that if you close this Jupyter instance, it's gonna delete the work that's in there, except for whatever was saved locally. So all the exercises and stuff we did, those are saved to your local machine. And in this README at the bottom, there are some shutdown procedures. Here, workshop shutdown procedures. If you wanted to get rid of all the material that we were working with, free up that space, there's information on how to do that and delete the container that we were using. Yeah, there's exercise solutions as well for that notebook that I just showed for size flows. So hopefully if you're interested, you can kind of follow along later today throughout the workshop. I'll be around if you have any questions. Cool. Thanks, everybody.
You update your original velocity model and you have like a final velocity model, which is the format of that velocity model.
So the question was, once you update your velocity model, what is the updated model format?
Yeah.
And it's the same as your input model. So in this case, for size flows, it's these Fortran binary files. So it's the same format as your initial model. Yeah. And then you can export that to, I guess, what a format that you would like. All right. Lunchtime. Cool. Thanks, everybody.
close Zoom? Is it recording?
I'm not sure. I think it's cool. Thanks, everybody on Zoom. I think we're going to start again at 1 o'clock. In one hour. No, is it 1 hour for moment tensor uncertainty quantification M2Q with Julian Turin. Thanks for joining. See you in an hour.
It's great to have the local option, so don't have to think.
Yeah.
You know, showcase today.